Tonight I want to go through the complete the square process with this quadratic that has complex coefficients. Now, you guys have all seen this famously confusing constant I. I've seen it defined both ways. Okay, so just keep in mind as we go through this, I is the same thing as square root of -1, or I squared is equal to a -1. All right, now the idea behind completing the square is just to take half of the coefficient. Now, if this is just a regular scalar constant, taking half is easy. It's a little more involved when you take half of a complex number, and that's exactly what I did right here. And I'll just write it off to the side here. If we have 10 plus pi force I, okay, divided by 2, we get exactly this, okay? Which, if you remember what you do when you're completing the square with regular real numbers, you take half of the coefficient of x. So that's what I did right here, okay? All right, and then the rest of it follows pretty naturally just from the standard algebraic identities here. Won't spend too much time. You have to subtract this constant off because it generates an extra constant. It gives you this term right here gives you this and this, okay? However, it has an additional constant term squared that has to be accounted for, so you subtract this exact constant term away from the entire object here. Just exactly like you do it when you're dealing with real numbers, okay? And then the rest of it's a little multiplying all this out. Won't go through each of those steps, but you end up with this statement right here, very akin, okay? We get x is equal to this complex number plus or minus the square root of some other complex number, okay? Now again, if we were dealing with real coefficients, you would be able to just write down the square root. If it was a perfect square, you'd do it. If it wasn't, you'd leave it in square root form. But we still have quite a bit of work ahead of us to determine the square root of this complex number, okay? So I do something that's relatively standard. We let a plus bi equal to the square root of the complex number of interest. Then we square both sides, okay? We square both sides to remove the radical. And again, when you square this, it's a binomial. And remember right here, this minus b squared arose from the fact that bi squared, remember I squared is -1, and that's what this term is. That's where this minus sign comes from, okay? And then the plus 2a/bi is exactly what you get when you expand this out, okay? So we'll carry on here. And y'all, again, I'm not going to go through every bit of minutia in terms of simplifying this stuff, but we get that b is equal to minus 5 over 4a from these two statements, all right? And then we substitute that. We substitute b is equal to minus 5 over 4a right back into here, okay? And then we end up having to multiply by a squared to get it simplified. And again, y'all, I left out some of the details. Hopefully I showed enough for you to follow along and believe me. So again, we did a substitution. We took this b, put it here and here, okay? All right, and then to get it in a more manageable form, we multiplied through by a squared because there would be, one of the terms had a squared in the denominator, all right? So we get this quartic equation with a missing third term, which means the sum of all the zeros have to add up to 0, which is a nice thing to know because notice all these zeros do sum to 0. There was a lot of guessing and checking going on right here. You may think this is mistaken because 2 is not immediately apparent, you know, the rational zero theorem. You don't think of 2 as being a factor of 25 over 16, but do note that 25 over 16, and this is kind of confusing, you know, it's not the normal rational zero result. You see, this is equal to 2 times 25 over 32, right? So you see, it's okay. It's just not quite normal. I think there's teachers that would get screwed up on this. You know, it's legitimate as far as the rational zero theorem goes because any factor of the constant term, as long as you have a monic right here or 1 right here, is a possible candidate for a rational solution. And sure enough, 2 turns out to be one of the rational solutions in -2. And also, this took quite a bit of work to show this, and I left every bit of it out. Okay, it's not too much trouble if you just do synthetic division, but there's not. I don't want to mess with showing you that. Now let's keep going. So y'all, what we did right here, this is just the original setup we had, right? And we concluded that A was 2. And let's go ahead and write down, just right here, let's write down B is equal to minus 5 over 4A, so you'll see where everything's coming from. Because it may get off the screen here in just a second. Okay. So B is equal to minus 5 over 4A. And you can kind of see where everything came into play right here. A equals 2 gives you this statement right here. Showed a little bit more detail here, but you actually get x is equal to 7 as a solution. Okay? And remember, you can just remember that if b is equal to minus 5 over 4a and a is 2, this is what happens. And you guys can verify. I've doubled and triple checked. I'm pretty sure I got it all right. Now, for a equals minus 2, it's very, very similar, except we get a complex solution. Okay? Now, remember, we had a second degree equation. You see down here? This is the equation we started with. If we find 2 solutions, we know we're done, right? The quadratic has no more than 2 distinct solutions, right? And so we don't really even have to check this purely imaginary pair of solutions. Okay, that's kind of nice. Since it's a quadratic, we've already found 2 solutions. We don't have to bother with this, right? I guess you might call it extraneous. I'm not sure. Anyway, these are the 2 solutions, 7 and 3 plus 5 fourths I. Now, this is our original equation. And again, I didn't, you can, this one's real easy to see right here that this is equal to 0, because if you put this, you see you have 7 right here, so that's 35 fourths I minus, right? You have minus 35 fourths I right here, but here's a plus 35 fourths I, so they cancel. And then right here you have 49 minus 70, which is minus 21 plus 21. So it's very easy to see that 7 is a solution. And also, it's not as easy. It's fairly easy, albeit tedious, okay? But also, this one works out too. And there's a little bit more work to do here, remembering I is equal to the square root of negative 1. But this also works out to be equal to 0, okay? So again, here's an example where the complex zeros don't occur in conjugate pairs. And remember, that's slightly trickier. Normally, you expect complex zeros to occur in conjugate pairs. But notice, if you just recall, this is a fairly instructive. That's for polynomials with real zeros, right? Real coefficients. We don't have real coefficients here. We have complex coefficients. So the complex solutions do not have to occur in complex conjugate pairs. So that's kind of subtle, and you don't see many of these really. The high school teachers and most of the college teachers, they just give real valued coefficients. So it's kind of fun to see the complete the square process work with complex coefficients. Okay, so again, our 2 solutions. Let me come down here. 7, and then 3 plus 5 fourths I. Okay, thanks for being.